going to tell you a story. Like you just heard, I was kind of responsible for some of the early steps of this semantic web journey. And I'd like to take a look at the original vision and the early days and kind of figure out what went right and what didn't, and how can we kind of reimagine this whole thing. In some ways, I'm reimagining, but I'm also kind of reinterpreting the original vision. Okay, so this is all old news now, so you just heard these. So I will say a few words at some point about Amazon Neptune, which is a managed, highly scalable graph database. But that's not really the main focus of this talk, and this talk is not a sales pitch for Neptune. What I'd like to start with is to look at kind of the sort of the long view of these technologies that we're dealing with. And some of you may have seen this. I've used this slide before, but I kind of really like the way this sort of shows that we're not talking about anything new. I mean, I often talk to our customers, and customers make these references to these new technologies, and I'm like, yeah, these are not new. So we can go back at least to the 1730s for both the inception of graph theory and the idea of ontologies in some sense, because Carl Linnaeus, the same year that Leonhard Euler published his work on graph theory, Carl Linnaeus published his work on the taxonomical classification of plants and animals, and so these are kind of the starting point. Of course, we could probably go even further back from there. But long story short, a lot of things happened. And these two things come together at the end of 1990s, and so we build this idea of the semantic web with all the kind of associated specifications, RDF, OWL, and what have you. And then fast forward another 20 years, and now we have modern knowledge graphs and graph databases, and semantic web. And those technologies kind of form the foundational underpinnings of these things. So what I really would like to now talk about is this journey that has taken place in the last 20 years or so. And so I'll talk about the original vision, and then I'll kind of try to reinterpret or reimagine what semantic web is today, and then say a few words about how we in the Amazon Neptune team see the way forward from that. So let me first talk about the semantic web, and I feel like I need to say a few words about, sort of from my viewpoint, about what the early history was that led to the semantic web vision. So to me, the pivotal moment is sometime in the fall of '96. Tim Berners-Lee comes to my office at MIT and asks me what I consider to be a very fateful question. So he asks me, he wants to know what I think is wrong with the web. And of course, this is a scary question considering who's asking. And my response to him was that web was built for humans, and so human interaction, human interpretation is needed to make the web useful. But I would like to build automated systems, agents, or whatnot to do things on the web, and I can't do that. And he gets very excited and says, "Yes, that's it. How do we fix that?" And I said, well, what if we look at knowledge representation and those technologies and see if we could apply them here to bring kind of data to the web. He gets even more excited and he leaves my office, and when he's at the door, he turns around and he says, okay, now you do it. So I spent the next year kind of brainstorming with a bunch of other people, and we found a lot of people who already had been kind of thinking about this stuff, and it led to the beginning of the work on RDF. And then it took us quite a long time, but in 2 years later, RDF became an official W3C standard. And so then Tim and Jim Handler, who was at DARPA at the time, and myself, we at some point we sat down and started thinking about, okay, can we write down sort of a broader vision of what all these things mean? And we did that and got that published. And at the same time, DARPA, which is the U.S. Department of Defense's research agency, started pouring quite a bit of money into research on various aspects of the semantic web, and then that in a way sort of led to the proliferation of the W3C specifications in this area. OWL most notably came from the DARPA program. So let's look at the original vision, and so here I have kind of the old web, and then the new semantic web, or whatever you want to call it. In the old web, it was a web of documents, and semantics of things were kind of implicit or hidden. And the semantic web vision basically says that we want a web of data, particularly where semantics is explicit and is accessible to the agents that are interacting with the data. The old web was strictly for humans. The new one was supposed to be humans and automated agents. I think the really big thing that happened was that the nature of standardization changed. So the old way of doing things, and this of course applies beyond web itself, standardization usually happens that you anticipate everything about the future, and then you standardize that. Kind of what are the things you can say and what do those things mean? But the semantic web doesn't rely on that. And in fact, we can apply something that I like to refer to as the delayed semantic commitment, and I'll come back to that in a second. And of course, the nature of knowledge representation also changed. Earlier, we had these centralized systems, and this, in a way, sort of means a shift towards more decentralized architectures for knowledge representation. So let me now try to kind of characterize all this. So a lot of people sort of said, "Oh, this is a new vision for the web," but I don't think that's quite right. It's not a new web. So what is it then? So let me edit this a little bit. So is it knowledge representation for the web that could give us proper metadata, digital libraries, better search results, maybe, things like that? That's really not it either. So I think the correct characterization of the semantic web is that it's knowledge representation using web technologies. And the reason for that is that the web technologies are well understood, they're well supported, they're widely deployed. And a lot of time has passed, and many people either are too young to know this or have already forgotten what a horrible difficulty it was to get networking working between organizations, between companies. And once HTTP shows up, now all of a sudden we have fantastic networking. HTTP goes through firewalls and things like that, and everything is a lot better. So that was a big shift and made it a lot easier to build distributed systems. The whole web has kind of this prevailing mindset of distributed systems. But let me edit this a little more, because it's not so much about distributed systems alone, but it's about sharing. It's about sharing information. And I think that's the sort of the key thing here. Now we have technologies that let us share data between organizations. So I already alluded to the change in the nature of standardization. So we specify semantics in a different kind of way now. We basically give people means to define and communicate semantics rather than saying these are the semantics that you are to adhere to for a particular standard. And I think that this kind of leads to what ends up being, in my mind, the key aspect of the semantic web, which is some type of serendipity. You can build systems and you can have serendipitous behavior. There are things that you may not anticipate, and in a way, the semantic technologies provide you solutions for those use cases that are yet to be articulated, as funny as that sounds. And so here's where the delayed semantic commitment comes into play. So you can build systems, and these can be driven by data and the definitions of data in a way that they can exhibit new behaviors later on as the data changes. So what worked and what didn't work? So I'm talking about the semantic web vision and generally, and then of course RDF and the related specifications more specifically. So I think that things that were good, we have strong global identifiers for things, and this is important when you're building representations and when you're building graphs. You also have predictable graph merging, and this is no small thing, because it makes sharing a lot easier. We have a simple schema language, and generally we have self-describing data where the ontology or the definitions for semantics can either be embedded in the data or they can be easily referenced. Mind you, there are some asterisks in this. I will come back to those things to kind of clarify some of these things. So what didn't work quite the way we would have wanted? So the original vision talks about the services that will emerge and publishing of data, and the idea that we open these endpoints that let people kind of query things. Now, of course, the vision predates Sparkle, but the general idea is that you would make data available for easy access. Once Sparkle shows up, people start thinking, oh, we'll just open these Sparkle endpoints, and but it turns out that Sparkle is kind of pricey to run, and there was no working business model to do any of this. So I think that didn't quite work out. And also Sparkle, and I'll explain this in a minute, I think of Sparkle both as a success and a failure. And then we sort of sketched this, what we now call the semantic web layer cake, building these technologies in a layered fashion. The upper layers never happened. Nobody ever built those. So there was supposed to be a layer for trust. We were supposed to exchange proofs of things, logical proofs, but none of this has ever happened. And then a more practical thing about RDF is that RDF really doesn't have usable composite data types, which turns out that makes it difficult to write software. But if we look at these two lists, and particularly if we look at the list on the left, what was good? So all these things talk about really sharing. How can we share data, share information between parties? And also, we shouldn't forget that the word semantics really wasn't in any kind of popular vernacular before this, and now it has become quite commonplace. And ironically, most people actually don't know what it means. sort of in the context of what I'm talking about, the way I think about semantics, and I take a very, not necessarily a very formal view of this, is that semantics is really definitions of how software can interpret data. So if you're able to communicate not just data, but also semantics, then the receiving end can actually take data that it hasn't seen before and make some meaningful use of that. And this is sort of the general direction where I'd like to see things going more and more. Okay, so let me clarify some of those points that I made earlier. So simple schema language. So some people would say, no, that's not the case. And so first we had RDF schema, and then along comes OWL, and OWL, of course, is great. It's more powerful, more expressive. But experience shows that OWL is really difficult for users, and it's actually quite poorly understood. In all this, we made the open world assumption, and I think that was the right choice, particularly when we're talking about open sharing of things. But I think that people building concrete systems also want to think in terms of a closed world. And so now we have Shackle, which in a way sort of introduces a more closed world to this. But the end result is that we really have 3 schema languages, and people are very confused. So what are they supposed to use? I actually get these questions all the time from our users. So then there's Sparkle. I think it's both a success and a failure. The first version of Sparkle definitely was an utter failure. And here's an interesting example. When the work was going on, I pointed out to the working group that they should have some type of support for paths in the query language. And the response, and this is verbatim, the response that I got. They said, paths are not a use case for graphs. They really said that, which I find quite puzzling. So, of course, the Sparkle 1.1 is a lot better. There's some support for paths. And, of course, a lot of other things like federated queries and whatnot. But Sparkle has no means of actual path discovery. So let's say you traverse a graph and you come to some node that's interesting. Sparkle cannot tell you how you got there. And I think this is a huge shortcoming of the query language. Also, from experience, we know that developers really want very little to do with Sparkle, if anything at all. I don't quite understand this, why that is, but that does seem to be the case. And then finally, composite data types, so things like lists and maps and what have you. In RDF, we basically decided that those kinds of things would be constructed using the graph structure itself. And this makes it very difficult to write any software that uses those. I think we should have provided proper abstractions and proper interfaces in the query language for these kinds of things. I really think we messed this up, and I'll show you why this is. So here's some code that I wrote last year. It's Python code for simply modifying the items of an existing RDF container. And that, in fact, this is not even all of the code that I had to write to do this. And this is, I think this is horrible. I mean, I think I did a decent job writing the code, but the fact that I had to write this much code is horrible. So I think this is, really unacceptable. And so we need to somehow fix that. So So we had this vision. Some things work, some things didn't work, and now we've come to the current day. And so what do we have today? So we have modern knowledge graphs, and in a way, I'd like to now talk about this in terms of that there is this new semantic web somewhere there. So I absolutely want to recognize that the life sciences industry was a big early adopter of the original semantic web technologies. But today we see much broader adoption in all kinds of industries, and in a way, so graph databases have kind of entered the mainstream. We also have these new technologies, so called labeled property graphs. And these are things that came about sometime in the last 10 to 15 years by people who either looked at the semantic web stuff and decided that was no good, or just otherwise decided to ignore it, or were not even aware of it. I honestly don't know. But so we now have these new kinds of graphs, and which we need to somehow deal with. We have a lot of new popular use cases for graphs in general, and for semantic web technologies particularly. Data integration remains sort of a general use case that we see a lot, but also things like fraud detection, identity resolution. A lot of companies are building these, what they call customer 360 solutions, which give them all the information in a single glance about a particular customer. There are also healthcare companies building things that they call patient 360 to gather all information about a patient, their history and whatnot. And of course, we have use cases now that also require new kinds of AI techniques. So we've had this kind of miraculous success of non-symbolic AI techniques, machine learning, statistical AI. And we see integration of these techniques into graph-based applications, and thus use cases like recommendation engines, for example. I sort of look at this as a broader interpretation of the idea of reasoning. We have the old classical symbolic reasoning, and then we have statistical ways of doing reasoning. And in fact, in the Neptune graph database service that I'm part of, the team that is building that, we have integrated with various machine learning tools, so that the graph data can be used for training machine learning models, and then those models can be used for things like predicting new links in the graph, or doing classification or whatnot. So let's look at the kind of the old semantic web versus the new semantic web, as I'd like to think about it now. So for the old one, the scope was the web at large, and I think that we more and more see these things where the scope is really an organization, an enterprise. For the original semantic web, we imagine humans and agents would be interacting there, but the agent part really didn't happen. So I would say it's humans and cloud services today. For the sources of data, we just basically imagine that, okay, the data comes from the web, without being more specific. Today, people are building noise graph applications, and the data has to come from the existing data that enterprises hold. So typically that means relational databases and maybe some other sources. And as I already said, we broaden the view of what the AI we can use from simply the symbolic techniques to both symbolic and non-symbolic. So the modern knowledge graphs, and here's my shameless plug for a book that I published last year. But so we have this organizational context now, organizational scope, and we talk about enterprise knowledge graphs. And there's a good reason to use that term. Oftentimes these systems are actually introduced to kind of clean up the mess that exists with existing enterprise data, to do data integration and to provide something that could be called democratization of data. So give people access to the data without people having to be database experts. And we also see the emergence of kind of these organizational upper ontologies. One of my previous positions working for a company called Nokia, I helped build one of these company-wide upper ontologies, and those serve as the enabler for company-wide data integration. I think I see systems like this often built as closed systems, and I think it's kind of a mistake. And the reason why I think it's a mistake to build these as sort of strictly closed systems is that as soon as you then want to bring in data from outside, it becomes an engineering proposition. Whereas with the semantic web technologies, we already had good mechanisms available for merging things, for getting new data from outside, and do all that. So now let me say a few words about the labeled property graph, since I kind of mentioned those earlier. So this is a different kind of way to look at the graphs. Things that we've seen is that these are, in a way, sort of closer to the developer mindset. They tend to have better programming abstractions and better interfaces. Oftentimes, these graphs are characterized by people saying that you can do edge properties. So you can put properties on edges in the graph. But I think this is kind of selling them short. This is not all that they are, although it is an important feature. And so also the query languages for labeled property graphs tend to support pathfinding or path discovery, something that I already mentioned is non-existent in Sparkle. So these are all good things, but there are a bunch of things missing from these labeled property graph systems. Here they are, and if this list seems familiar, there's a good reason for that, because these are the things that I think exactly are really good about semantic web technologies and RDF particularly. Strong global identifiers, predictable graph merging, actual schema language, and the ability to build self-describing data. Now, since I mentioned edge properties, some of you who are thinking about RDF think about, well, what doesn't RDF have reification? What about that? So most importantly, note that I did not include this in the list of things that did not work. Reification is an incredibly important part of RDF, and funny enough, when I was preparing for this talk, I went back to look at the original first public working draft of RDF, not the first actual standard, but the first time we published a draft, and that was in October '97, and the whole idea of reification shows up in like almost immediately in that document. And then when I looked at consecutive working drafts all the way to the first specification, the discussion of reification tends to move further back in the spec. Nevertheless, it's important, and then unfortunately, it's also kind of widely misunderstood. And if all you really wanted to do was edge properties, then reification is kind of a scary word. So we have this new W3C working group ongoing, which I am chairing, called RDF Star. And our goal is to really kind of fix reification so that it becomes a more usable feature of RDF. And it will bring us closer to the labeled property graphs in some ways, although it will not get us quite there. But so some people might now think, well, okay, so we have graphs, and graphs are graphs, right? But it turns out that so when you're building knowledge graphs, you typically need what the semantic web technologies have to offer. You want ontologies, you want graph merging because you're bringing data from different sources and things like that. But there are other graph applications as well. And oftentimes when I look at these, it's like the graph is really treated as sort of a very large and potentially very complex data structure. And of course, that's what we've done in software engineering forever. We have data structures, and then we write code that manipulates these data structures. And these modern graph databases now give us a better ability to do that. But what we really have is we have sort of a rift between these two things. And what it really means is that we're looking at graph as a logical representation of data versus graph as a literal data structure. RDF does the former, labeled property graphs do the latter. What I would really like is that when I'm building a knowledge graph, I might also have the need to apply graph technologies that are better served by these labeled property graph systems. And so, the Amazon Neptune graph database actually supports both RDF and labeled property graphs, but it's kind of an either-or proposition. It doesn't support them simultaneously. So when you start using Neptune, you have to choose which kind of graphs you're going to build. And we find that this is a sort of a tremendous source of confusion among our users and customers. I get this question all the time, which one should I choose? And sometimes there is a very clear answer to that. And sometimes the answer is not so clear. And generally, I would not like to talk about it at all. So what we have started in our team is this long-term project that we call One Graph. And the idea is to really bring RDF and property graphs close together and provide kind of graph interoperability, if you will. The solution for this is not going to be easy. Like I already said, RDF Star is a significant step in the right direction, but may not quite get us there, and so we need more. Some of you may have realized the name of this project is a Tolkien reference. One graph to rule them all. My boss felt that name is way too arrogant, but we went with it anyway. So more technically, One Graph is a graph meta model that will unify RDF, RDF Star, and some flavors of labeled property graphs. And in this construct, the existing graph meta models like RDF are kind of lower dimensional projections of One Graph data. And so we can have these round trips. We can go from RDF to One Graph and then back to RDF, and that's a lossless round trip. But of course, the round trip from arbitrary One Graph data to RDF and back to One Graph may not necessarily be lossless. But the first case where we go from RDF to One Graph and back to RDF, that being lossless, serves an important purpose. Of course, the practical challenge that we've discovered is that RDF and property graphs are used very differently. And so the real challenge for us is to kind of try to reconcile this. But the big goal is this graph interoperability, which to me means that there's no more customer confusion, and it's easier for me to talk about graphs. And once we're done, and this is a long-term project, so we don't have a concrete timeline for this yet. But once we're done, there will be benefits kind of on both sides of this rift, if you will. So first of all, those things that are good about RDF and Sparkle and whatnot will now become available for property graph users, and they don't have to reinvent these. Because we see a lot of this where people are using property graphs and they're kind of reinventing things that already exist on the RDF side. There will be no more complaints that RDF doesn't support edge properties, obviously. But what I really like is that now we can do proper path discovery. And we don't have to necessarily fix this in Sparkle, because we can now we can do this round trip. We can go from RDF to OneGraph, use the query languages available there, labeled property graph query languages, do path discovery, and then basically circle back to RDF. And then, of course, my personal favorite, I really like the query language Gremlin, and would like to run Gremlin queries over RDF. And this becomes possible. So that's sort of the way into the future that I see things happening. I think that the rift that we have today, where we have these two different kinds of graphs, is hurting the graph industry, if you will, as a whole. And so we can see much better graph technology adoption once this thing has been fixed. So in summary, we had this vision. Some things worked, some things didn't. Now we have the new semantic web, or the new interpretation of these technologies. But of course, we have a lot of new technologies and much confusion. So my hope is that the OneGraph project will eventually unify the graph landscape, and everybody will be happy. Thank you.
Hi, Ora. This is Frank van Harmelen from Amsterdam. So nice to meet again after so many years.
It has been a while. Yes.
Yeah. So you keep mentioning the term semantic web, and wouldn't you agree that of the semantic web, the semantic part actually worked out quite well, but the web was is dead. So yes, there's a lot of semantics, but in all of these papers at the conference these days here, it's a lot of semantics, a lot of companies doing semantics. We heard this afternoon. Nobody mentions the web.
Yes, that's an interesting way to look at it, but that's exactly the way it is. And like I was trying to say, it's not so much about web. We did use web technologies, which I thought was a good idea. But it ended up not being a vision about the web at all. In a way, sort of, you could say that there's kind of two things wrong with the term semantic web. So it's not about the web, and like I said, nobody knows what the word semantics means. Otherwise, it's a good term. Now, Jim, if you ask Jim Hendler, he would say that also the word "the" is wrong, because there's not a single semantic web. So.
Hi, Ora. It's Eric Pertamo. You said in that last slide, some second to last slide, that nobody was going to complain that there were no properties. No properties on
Edge
properties.
properties.
Right? I remember. As properties. That's it. Yes. If I pull the RDF into OneGraph and then throw some edge properties on some things and then pull it back out into RDF, can I still round trip? And
yes, RDF star will give you that.
Okay, so it's effectively it's nobody's going to complain about the lack of edge properties to the extent that RDF star gives me the edge properties that I want in RDF.
Right.
OneGraph isn't really giving them to me, right?
I'll tell you what the challenge here is. So RDF, an RDF graph is a set of triples, a set of statements, and a statement, let's call it SPO, is unique in an RDF graph. So so there can be only one, and so now if you want two edges labeled the same between the two same nodes, and you want to put different edge properties on them, which the label property graph people do all the time. This doesn't quite work in RDF. So this is still something that that we need to kind of work on from the RDF star standpoint. The old RDF verification mechanism, of course, could handle this just fine.
Yeah, a question on edge properties. There's been an alternative proposal, which is basically with the subjects and objects. You can type you can type the subject and say, you know, this is a something, but there doesn't seem to be any way to. I guess the best term would be gerundify or to instantiate the predicate, to reference the predicate as a first-class individual and say it's an instance of a generic predicate. Has thought been given to that?
Yeah, in fact, that idea has come up in the RDF Star Working Group very recently. I don't know exactly what we're going to do about that. One of the challenges that the RDF Star Working Group has to handle is that we can't come up with a specification that renders old RDF data invalid or unworkable, or we have to maintain backward compatibility. So the idea that you describe in itself is quite interesting and attractive. I don't know if we are able to accommodate that in the new standard.
Hey, when you talked about the original vision of the semantic web, you also talked about all of the standards. You know, there was a lot of standards developments in the 2000s. And then you talked about the modern and enterprise semantic web, or however you want to call it now. So thinking about the standards that we spent a lot of time and effort writing and reading from those times, which of those standards do you think are still relevant and important now? And which of them do you think need abandoning? Assuming any.
Well, I mean, RDF and Sparkle certainly are relevant. Sparkle is a good query language despite its shortcomings. And RDF, of course, is sort of the foundation of all this. I'm a little surprised, kind of the mixed success of OWL. I think that the things that OWL gives you are useful, but most people don't really know how to use OWL. Shackle, on the other hand, seems to be something that really resonates with people. So that's a specification I like. And then, since we need to populate these graphs from existing data, I really like the R2RML specification. I know that there can be different approaches to going from tabular or relational data to a graph, but R2RML is a good standard, and there are a number of implementations of it, and so it works. So those would be, I guess, my favorites.
Hi, Ora. I have a question regarding your perspective on Neo4j and their book that they called Knowledge Graphs, published in O'Reilly.
I'm sorry, and what is your question?
Your perspective on it.
Ah, yes. Well, I think I'm not really permitted to comment on that, because Neo4j being a competitor of my employer, and we generally have a policy of not talking about competitors. Now, on a personal level, I welcome any book that makes it that helps people build these knowledge graph systems and deploy them. And I think that there's plenty of room for any number of graph database vendors. I think that there are many more people out there who are not using graphs or graph databases who could really benefit from them. So we are happy to compete in this field. I think there's plenty of room.
Ora, I really enjoyed your talk. What do we do when these knowledge graphs get larger and larger to the point where the performance degrades substantially? How do we design these knowledge graphs for performance and scalability? Because we're putting data in them, but our ability to ask the questions that we need to ask is, well, it's getting harder and harder.
Sure. I mean, in some sense, I suppose it depends on what kind of questions you want to ask. But with Neptune, for example, the size of the graph is really not the dominant predictor of performance. So yeah, Neptune really can, in a performant way, answer questions even if the graph is very large. It depends on what kind of query you're going to be writing. Now, those queries would be ones that sort of touch a relatively limited graph neighborhood. But if you're talking about things like graph algorithms that you want to apply to the entire graph and compute something, I think there's still plenty of work for all of us to do in that area. I don't have any kind of silver bullet for that, unfortunately. My apologies.